My name is Shariq Haseen, and I work with Dr. Peter Kroll. The topic of my presentation today is about developing reactive force field parameters for simulating silicon carbonitride polymer-derived ceramics. Polymer-derived ceramics are advanced ceramic materials with a list of notable properties and application in a variety of commercial fields. With the right range of pyrolysis temperatures, polymer-derived ceramics can be described as a mixture of an amorphous glassy matrix with an embedded free carbon phase. We are particularly interested in the structural features of the free carbon phase. In atomistic simulations, the extent of the free carbon phase is limited by model sizes. Smaller models can exhibit spherical agglomerations, while larger models can exhibit interconnected tubular networks. Highly accurate quantum chemical calculations can be used to investigate polymer-derived ceramics, but they are limited in the size of the system they can compute. Thus, we parameterize a classical reactive force field, REACs, for performing million atom simulations with accuracy comparable to quantum chemical calculations. So we train REACs parameters to investigate silicon carbonitride polymer-derived ceramics. Our focus is on training silicon nitride or silicon nitrogen and silicon carbon nitrogen parameters. Using our extensive library of silicon nitride and silicon carbonitride structures, we train parameters to reproduce quantum chemical energy differences and forces. Resulting parameter sets are refined through a self-learning process. Next, we evaluate our parameters. So we calculate mechanical properties for alpha silicon nitride. Calculations of energy volume curves on the left and stress strain curves on the right in the section indicate that REACs agrees well with quantum chemical calculations. Consequently, the bulk modulus and shear modulus also agree between REACs and quantum chemical calculations. In terms of energy correspondence, we seek to achieve a one-to-one correspondence between REACs and quantum chemical energy differences. Thus, the closer to 1 the slope of each data set in this section is, the better the energy correspondence. Energy correspondence for silicon nitride is fairly decent, although the R-squared values indicate strong correlation between the two. Moving past crystalline silicon nitride models, we also generate amorphous silicon nitride in REACs. Resulting amorphous models come out quite nice, and over-coordination and under-coordination of silicon and nitrogen is relatively low and typically less than 10%. Cycling amorphous models between REACs and quantum chemical methods results in REACs energies remaining mostly stable and exhibiting no significant structural changes. Consequently, there's a good correspondence between energy minima with both REACs and quantum chemical calculations for silicon nitride. Meanwhile, silicon carbon nitrogen parameters can be evaluated in a similar manner to silicon nitrogen parameters. The energy correspondence between REACs and quantum chemical calculations is calculated for two different silicon carbon nitrogen compositions, one with more silicon carbide than silicon nitride, and one with more silicon nitride than silicon carbide. Energy correspondence is pretty good, though it's clear that composition impacts the energy correspondence. With regard to high temperature behavior of silicon carbon nitrogen parameters, we calculate self-diffusion within REACs for silicon nitride, silicon carbide, and silicon carbon nitrogen with the indicated composition. The diffusion of silicon carbon nitrogen is found to be between the diffusion of silicon nitride and silicon carbide, which is what we expect. Additionally, our parameters, which I'll refer to as UTA REACs here, produce forces very close to quantum chemical calculations in simulations of silicon carbon and nitrogen with free carbon at 1500 Kelvin. Existing parameter sets like those from Kulkarni produce forces that substantially deviate from quantum chemical calculations. Overall, we find that our REACs parameters are pretty good for silicon nitride. Silicon carbon nitrogen parameters are also good enough to exhibit good energy correspondence between REACs and quantum chemical calculations, although describing several different compositions of silicon carbon and nitrogen with the same set of parameters is a challenge. Simulations of silicon carbon nitrogen at high temperatures reproduce diffusion and forces well. The next step is to optimize hydrogen parameters in order to perform simulations with polymers.